Thank you
audio
very
side.
much, everybody, for joining today. So it's the June edition. So today we have invited two speakers. First, we have Nathan Peck from AWS. He's a senior developer advocate, and he's going to talk about tools for building modern containerized applications on AWS. Welcome again, Nathan. Thank you again very much for accepting our invitation.
Thank you very much. As introduced, I'm Nathan Peck. I work as a senior developer advocate at AWS. And so I want to talk about a little bit about containers and container orchestration and infrastructure as code tools. All of these things being modern tools for building out a containerized application on AWS. So the agenda is I'll start with an introduction to containers themselves, as well as container orchestration, to make sure everybody is up to speed on what AWS is offering and what containers are and why you might want to use them. And then I'll talk a little bit about infrastructure as code and specific the progression of infrastructure as code, how things started out, and then how more and more advanced tools have been built, finally leading up to AWS Cloud Development Kit, which is probably one of the most sophisticated and interesting infrastructure as code projects I've ever worked with. And then I'll talk a little bit about how AWS CDK makes it easier to build a containerized application. So let's start out with that introduction to containers themselves. So when you think about building an application, if you're writing code for an application you want to run on your development machine or really anywhere, you'll realize that the application is built out of a lot of different pieces. So your computer has the operating system on it. So in this case, let's say Ubuntu is an operating system. Then you have a runtime to execute your code that you're writing. So in this case, I've put down the Node.js runtime, but let's say you're writing Python code, that would be the Python runtime. If you're writing Java code, you might have a Java runtime. You need something that will actually run your code for you. Then you have different libraries to work with in your code. So for example, if I'm writing a Node program, then I probably install something from NPM. If I'm writing a Python program, I might install something from PyPy or something like that. And then you have your actual application code. And so when you combine all these pieces together, then you have a running program which executes on your machine and things function. But there's a pretty common problem that pops up when you're working in a distributed team with multiple people. And that's this problem of the code worked on my machine, but then it didn't work when somebody else tried to run it. And it ends up with multiple developers facing this problem of why can't we get this code to run reliably? Ideally, you want reliable results every single time you run your code. It produces the exact same results, and it produces the exact same results no matter who runs it on which machine. And the reason why you often have problems is that there's configuration drift between different machines. So for example, in this example, I've highlighted two different developers, and it turns out they're running different versions of operating system. They're running different versions of Node.js runtime. And one developer forgot to run npm install to have the latest version of the dependencies. And then one of the developers is also running code from a different branch of the code repository. And so you end up in this situation where the more pieces that are being put together to make this application run, the more likely you are to end up with someone doesn't have the exact same installation environment as everyone else. And as a result, things don't function properly on their machine. So Docker containers are a solution to this problem. They provide a way to gather up all the dependencies that are required for your application to run in one package. And the way they do that is using a Docker file. So a Docker file, it's nothing scary. It's just a little text document that contains a list of commands that you would need to run in order to build out the environment to run your code. So in this case, I've included an example Docker file. So it's starting from Ubuntu 2004. So it's starting from the latest version of Ubuntu. And what this does is it grabs a image copy of Ubuntu operating system to start from, and then it runs some Ubuntu installation commands to add the Node.js runtime engine. If you're working with Python, for example, you could easily substitute in there a command to install the Python runtime. And then I'm adding my package.json file, which is my manifest that describes what packages I want to install. And then I'm running npm install. So that's grabbing those dependencies out from npm. This could just as easily be adding a requirements.txt file for Python and then doing an installation from the Python package manager as well. And then last but not least, it's adding the code and specifying the command that's required in order to run that code. And so because I've written this Docker file, it provides me with a way to grab all of these things that are required for my application and package them up into one piece that I can distribute. And so what ends up happening is the same container can run everywhere. So developer A, there on the left, can run that exact same container as developer B. And I can also run that exact same container on a testing environment or even a production environment as well. So whether I'm running it on my local laptop or if I'm running it on a server in the cloud or wherever I'm running it, this container is going to run the exact same way in all these different places because it has the exact same version of everything that I've added to the container. So a couple important Docker commands to be familiar with if you decide that you want to work with Docker, if you're new to Docker, is Docker build, Docker push, Docker pull, and Docker run. So Docker build is the first one. This is the most important one that kicks everything off. This is where you've written out your Docker file, like the Docker file that I showed on the last slide. And we want to take that Docker file and run through those commands to generate a container image. Docker push is how you take the container image that you've built and upload it to a registry on the internet. So this provides not only a backup of everything, but it also allows you to easily distribute it, for example, to your other coworkers or distribute the container image to. Then Docker pull is used on the other side to download the container image back out of the registry. So you can think about Docker push and Docker pull kind of like the equivalent of a git push and git clone, if you're familiar with the git tool. Then last but not least, there's Docker run. So once you've pulled a container image out of a registry, you want to run that container image on your machine, you use the Docker run command. So to summarize the life cycle, you start with your code on your computer, and you probably have a folder of code and some other tools that you want to package up. You use Docker build command to package that up into a container image. And then that container image travels to another machine, and then you use Docker run on that machine to actually run the container image, which runs the application on that machine. So now we have a high-level understanding of what containers are and what they do for you. Let's add the next piece, that's the container orchestration. So you saw the four key commands of Docker: the Docker build, Docker push, Docker pull, and Docker run. And you can imagine that that's pretty easy to work with if you have only one developer laptop or a couple developers or even just like a couple servers in the cloud. You just have this, let's say, one container type that you're working with, and you have a couple hosts. But things get more complicated fairly quickly. Let's say you have multiple applications you want to build. You have one Node.js application, and you also have one Python application. And you have a few different hosts in the cloud or on the developer laptops. And then eventually, let's say you have a bunch of different applications. Now I have some Rust applications, I have an Nginx web server, and I have even more hosts. You quickly run into a situation where it's complicated. You find yourself wondering, how do I get containers onto all of these servers, all these hosts? Am I going to use SSH to all of these different machines and tell them to Docker pull and Docker run? And what happens if something fails? Is it going to automatically retry? What if when this application container just crashes? And then you also find yourself wondering, how many servers do I need to run? Let's say I have 10 different applications, and each of them has a different load. Let's say some customers are using the application very heavily, or other applications get very little traffic. You need to find a way to adjust to growing and lessening traffic demands. And then when you do have a big pool of servers in the cloud, you find yourself wondering, what happens if I need to add or remove a server? Let's say a server is out of date, needs a security patch, I need to reboot it or something like that. What if there's applications running on that server that need to stay up and running for my customers? So container orchestration is intended as a solution to this problem of the growing complexity of managing multiple applications across a pool of multiple servers and multiple developer machines. And the basic concept is two parts. Part one is telling the container orchestrator that here is my container image that I want to run. And then part two is giving the container orchestrator a command about how many copies of the container you want to run and how you want them to run. And so there's two, or rather three key services that you can put together for the AWS native container orchestration stack. So the first one is Amazon Elastic Container Registry. This is an image registry in the cloud. And this is where you say, here's my container image I want to run. So once you've built your container image locally based on the applications on your laptop, and you do that Docker push and Docker pull command, you would do that to Amazon Elastic Container Registry. And Elastic Container Registry, or ECR for short, is the storage point for any container image that you build. And then once that container is uploaded onto the Amazon cloud inside of an Elastic Container Registry, the next step is to actually run it. And so Elastic Container Service provides an easy-to-use API from AWS where you can 5 copies of my application container. And you can start out with a command that's just that simple. Then you can also add more complexity as well if you want to. So, for example, you can say, I want high availability. So I want to distribute those 5 copies across 3 different availability zones. And then you can also specify other resources in the cloud that you want to connect to your container. So you can say, my container has a web service inside of it, and I expect it to receive web traffic. So I want to connect all 5 of these copies behind a load balancer. So that way when traffic comes in and hits the load balancer, 1 in 5 requests gets distributed to each of my 5 different copies of my container. And so then ECR and Elastic Container Service, ECS, are both utilized by AWS Fargate. And then our AWS Fargate is the engine which actually runs the container. So to summarize, showing the full stack here, image registry, its purpose is to store your Docker container right there in the data center where you plan to run it. ECS, its purpose is to be a management interface. So it's an API that you use to actually launch your applications. And this management layer is tracking your application state constantly and connecting the application to other resources like load balancers. And then last but not least, there's the hosting layer. The hosting layer is AWS Fargate. This is what actually runs your application container for you on demand. You don't have to think about capacity. You don't have to think about security patches or updates or anything like that. AWS Fargate is automatically patching the underlying infrastructure and things for you. So combined together, these 3 services make up the AWS native container stack. I just want to give a shout out right now to make it clear. This isn't the only way to run containers. AWS also has Elastic Kubernetes service, which allows you to use Kubernetes as the management layer. But the only thing that switches out there in this diagram is you would use Amazon EKS Kubernetes service as the management layer, but you can still use ECR as the image registry and AWS Fargate as the hosting. So going back to container orchestration on ECS, these are the four core concepts of container orchestration that you should be familiar with. The first one is the idea of registering a task definition. So the task definition is just a description of what application container you want to run and what settings it needs. So the setting might be something like, I want to run this on an environment that has 2 core CPU and at least 4 gigabytes of memory. And so when you gather up all those settings for how you want to run your application, it's called a task definition. And you register a task definition with your container orchestrator. The next concept is creating a cluster. So a cluster is just it's like a namespace. It's a grouping of applications and hosts to run those applications on. So the servers to run the application, they could be provided just as EC2 servers from AWS. But more often than not, most customers are choosing to use Fargate as the hosting service because that allows you to create a cluster without having to specify a lot of EC2 servers as capacity. The cluster essentially becomes like this infinite magic cluster that can run as many containers as you want to run on the cluster. So a task is just a standalone copy of your container that's running inside of the cluster based on a task definition that you specified. So if your task definition said, I want to run this container with 2 CPU cores and 4 gigabytes of memory, then when that task definition is put into the cluster, it becomes a running task in the cluster. And a standalone task just runs until the code completes and the container exits. But there is another type of program that you might want to build, and that's a web service. So when you're running a web service, the code doesn't ever run to completion and then exit. The code continues running forever. And so the idea behind a service is that the service is listening on a port, a network port for incoming traffic. And most often, people who are running a web service want to run multiple copies of their service. Because if you're just running one web server and that your customers are just getting an error when they try to load it up in the browser. So the idea behind service and container orchestration is to run multiple copies of your container as multiple tasks and then hook all of these tasks up to another resource, such as a load balancer or similar, to distribute traffic to all of these tasks. So now that we've introduced containers and container orchestration, let me launch into the infrastructure as code. And this is where things become a little bit less theoretical and a little more practical. I'll show some actual code examples of how to set this up. So the first level of creating infrastructure, and this is where most people start out, is creating infrastructure by hand. So here in this diagram, you can sort of imagine the AWS console. Some of you may be familiar with this console. Most people who start out with the console, and most small startups and small businesses, they start out by using the console by hand. They load up that console on their web browser, and they start clicking around inside the console on all the little buttons and text inputs and things like that to create the resources that they want to create. And so multiple people working together on the console in different areas of the console at the same time end up creating the overall infrastructure for your organization. Now, there's some pros and some cons to this approach. So on the positive side, creating infrastructure by hand using the console is great for your first exploratory infrastructure. Most of the time, you aren't necessarily super familiar with a new service, so you kind of need the guidance of the console to tell you how to set things up. And if there is an error, you see that error in the console really fast, so it helps you fix problems. But there are some major downsides to clicking around in the web console by hand as well. So first of all, it's slow. Imagine if you're creating multiple of the same resource, you got to go through the same workflow, clicking in the console over and over again. So long term, it's a bottleneck in your development speed of being able to create an application if you have to click around different things by hand in the console. And the other problem is it's pretty hard to reliably reproduce your results when you're doing things by hand. People don't have a high success rate at doing the same thing over and over again without making mistakes. They'll end up clicking on the wrong button somewhere in the interface or entering the wrong value. And then even worse, you'll end up in a situation where there's multiple people who are trying to work with the web form in the console, and they have different ideas about how to configure things. So person A changes the value to, let's say 1, and person B changes the value to 2, and then person A changes it back to 1. And so you have all these conflicts. Everybody has their own perspective on how they want things to be configured, and there's no one single source of truth. There's lots of different actors who are manipulating things inside the console, and so you end up with a lot of different results that happen. So a lot of times this leads to the next level of infrastructure as code, and that is called imperative infrastructure as code. So in this approach, we know that AWS has an API, and you can use that API to create resources on your AWS account. So a lot of people say, let's write a script. And what the script will do is it will call the API to create things on my account. And so what ends up happening is multiple people are all contributing to the deployment script, and the deployment script is what actually runs and uses the API to create things on your account. And generally, the deploy script ends up looking something like this. You have this pattern you'll see over and over again in scripts where you say, let's do a get resource to check to see if this resource exists. If the resource exists and it matches how I want it to look like, then I don't need to do anything. Otherwise, if the resource does not exist, then create the resource. Or if it does exist but it doesn't match, then update the resource. And so the deploy script does this basically over and over again. So it checks to see, do I have a service running? Do I have let's say I have an S3 bucket or something like that I want to create. It does the same check over and over again. So already you can kind of see there's a lot of boilerplate here. There's a lot of things I need to manage myself. Like what happens if something fails and I need to retry? There's the exact same time. You'll end up with a race condition. They may both end up creating a resource at the exact same time instead of creating only one copy of the resource. So to summarize the pros and cons of this imperative infrastructure as code approach, it's clear that if the imperative script is written well, it's going to be repeatable and reusable. So I won't have that problem of a human making mistakes clicking around in the console. And I can actually have multiple people who are working on the script collaboratively. So I won't have that problem of person A changing the setting and person B changing it back. But I have to write a lot of code to do this. It's a lot of boilerplate. I have to write the same pattern over and over again. And it can be hard to write this reliably. It has to handle a lot of different failure conditions. And there are still some weird race conditions where I have to be careful about multiple people using the script at the same time. Because if 2 people run the script at the same time, things can go wrong. So this leads to the next level of infrastructure as code. It's called declarative infrastructure as code. So in declarative infrastructure as code, there's a layer that sits between the AWS API and your intention about what you want to build. And this layer is a tool. For example, it could be AWS CloudFormation or HashiCorp Terraform. And the idea behind declarative infrastructure as code is that rather than explicitly writing code, you write a description of what you would like to create, and there is code which consumes your description and automatically calls the API on your behalf to create things based on your description of what you would like to create. So here's what that looks like. You can see in this document, it's written in YAML format, and there's a list of resources. You see that tag up at the top where it says resources. And then inside of the resources list, each resource has a name, and then it has a type and various properties. And so what this ends up being is it's just a data structure that has a list of items inside of it that have properties. And the infrastructure as code provider, in this case CloudFormation, is responsible for taking this description of what you want to create and turning that into a reality by making API calls. And you can see there's some more sophisticated methods in here, like functions called find and map, ref, things like that. So you have some capability to add a little bit of like smarts in here, but it's clear that there's not a whole lot of complexity in here for what you can do. So just to summarize how this works again, here I have a CloudFormation sample with a list of resources. And you see I have a resource called bucket1. And this YAML gets passed off to CloudFormation. CloudFormation calls the AWS SDK on my behalf. And then SDK results in the creation of a bucket in S3. Now, if I was to add a bucket 2 to this list, then what happens is CloudFormation makes another call to the AWS SDK and adds a bucket. If I remove bucket 2 from the list, then CloudFormation notices that bucket 2 is gone and instead makes a call to the AWS SDK to remove the bucket, and so the bucket gets deleted. So pros and cons of this declarative infrastructure as code approach. Obviously, there's not a whole lot of boilerplate in here because I don't have to manually write commands to create and update resources anymore. Instead, the infrastructure as code is going to do that for me. And I still have this benefit of being able to collaborate with other people. Multiple people can work on this template at the same time. I also have a really cool thing with CloudFormation, which is built-in conflict resolution. So if two people are trying to update the infrastructure as code description at the exact same time, the centralized CloudFormation, or maybe it's Terraform, whatever your provider is, the centralized tool handles locking and unlocking resources centrally, so that way only one person can be modifying things at a time. But there are some downsides. The first downside is that there's a one-to-one relationship between writing a chunk of file which describes the resource and a resource on your account. So it turns into a lot of description to write. In many cases, these templates can end up being thousands of lines long as you describe a full list of every single thing you need to create on your AWS account. And then there's also limited programming logic available inside of these templates. There's usually only a few built-in functions, and there's no concept of loops or reusable functions or anything like that built into the metadata programming language. So the result is you're limited in how much sophistication you can have to make things easy, clear, and maintainable. Instead, you basically have to use a lot of copy and paste. You have to write out, like I said, it could be thousands of lines of different descriptions of different resources you want to build. So these problems lead to the next level of infrastructure as code, which is, let me see if I can close this out. I was just clearing some of these annotations around the screen. Level 3, the AWS Cloud Development Kit. So with AWS Cloud Development Kit, you notice that this chain that I'm diagramming here is getting a little bit longer each time. There's more tools in the chain, which looks a little bit more complicated, but the end result is it's going to be simpler for you. So once again, we have developers and we have the infrastructure that you want to build, but now there's 4 pieces in between the developers and the infrastructure. So you'll notice the first thing that's new is AWS Cloud Development Kit, and there's a actual code file called app.js. So the idea with AWS Cloud Development Kit is you have multiple developers who are writing a piece of code in a programming language, and then that programming language utilizes AWS Cloud Development Kit. AWS Cloud Development Kit then generates that CloudFormation description of your infrastructure, and then CloudFormation makes the calls to the AWS SDK on your behalf. And then the SDK API calls result in your organization's infrastructure being created. So I'll show you now an example of what one of these scripts might look like. So the first thing you'll notice is that this is a much more familiar, if you're familiar with code, this actually looks like code. I don't anymore have like just a plain text description of what I want to create. This is an actual function call with classes and methods. And you also notice that it's a little bit shorter too. You know, I have my code coloration going on here. It's a little bit easier to read if you're a developer or a developer type. So I'm able to write in my familiar programming language. In this case, I've put a JavaScript code example, but CDK also supports Python and several other programming languages as well. And so the idea here is that you're able to create many different underlying AWS resources at once with just a single class inside of your code. So there's a stack at the top. You'll see class myService extends CDK stack. And inside of the stack, there's a list of resources called constructs. And each of these constructs could have a variety of different resources underneath them as well. So there's multiple layers to this. And depending on how sophisticated you want to go, you can go all the way down to the bottom layer, or you can stay at a higher level layer and just work with the high level constructs. So these things are still declarative. I don't have to write a bunch of boilerplate saying, if VPC does not exist, then create VPC. If it does exist, create VPC or update VPC. Instead, all I have to do is say VPC equals new EC2.VPC. And that specifies that I want a VPC to exist. By declaring that I want a VPC to exist, the VPC will be created when I deploy this CDK code. So let me show an example, zooming in now on one of these constructs to demonstrate what it does. So looking at that new EC2.VPC command, this is just one line of code here. But if you think about, if you're familiar with VPCs inside of AWS, they are fairly complicated. You're essentially defining a lot of rules for subdividing off a chunk, an isolated network on the AWS cloud. And so there's a lot of complexity involved with doing that. For example, you may want to have your virtual network on the AWS cloud divided across multiple availability zones. You're going to want internet access for that. If you do have a privately networked area inside of your VPC, you're going to want the things running inside this private, isolated, firewalled area to have internet access as well. So you need something called a NAT gateway. So here you get an idea of a VPC is not just one thing. It's made up of the sum of all these different parts, the different subnets, the internet gateways, the NAT gateways, and all the configuration required to connect these things together. So just to give you an idea of how much configuration is required, let's look at the cloud formation that's required in order to specify a baseline VPC. 270 lines worth of it. So that's quite a bit of cloud formation to write there. But when I use CDK and I say new EC2.VPC, it's just one line. That's all I have to write. And it goes ahead and it creates all of those resources and all of those 270 lines of CloudFormation YAML automatically. So that one line of, in this case, JavaScript code, or it could be Python code, will expand outward into that 270 lines of CloudFormation automatically for me. And I don't have to handwrite that anymore. So you can already sort of get a sense that this is a massive time saver for you, as well as just mental burden. I don't have to think about all these underlying configurations anymore. All I have to do is use a high-level statement like create a new VPC with max AZs 2. So distribute this VPC across 2 availability zones. So another cool aspect of Cloud Development Kit is that it helps with your local workflow as well. So if you think about it, there's certain tasks that you often need to do on your local developer laptop when you're developing an application. So let's say you're creating an S3 bucket in the cloud to hold files and documents of some sort. Just because you create the bucket in the web console or whatever tool that you're creating doesn't actually add files to the bucket. You still need to upload those files off of your machine and put them onto the bucket, so that way they're accessible inside of there. So CDK also supports doing operations locally on your developer machine, such as gathering up files. So here you can see there's a construct for the s3.bucket. So I'm saying my website bucket equals new S3 bucket. So what that's doing is that's creating my S3 bucket for me. But then I'm also creating something called s3 deploy.bucket deployment. So what this is doing is I'm specifying a folder full of my website files, probably my HTML files and CSS files and image files for my website. And the bucket deployment construct is automatically creating a zip file out of all of those files on my local machine and uploading it to the S3 bucket in the cloud via a Lambda function, which extracts that zip file on the other side into my S3 bucket. So you can get an idea that CDK not only creates resources on my AWS account, but it also helps me to streamline some of my workflows that I would normally have to do by hand on my development machine. Another cool aspect of CDK that I want to highlight is that all of these constructs that I've highlighted, the VPC construct, S3 deployment construct, and many more, they're all shareable and they're all reusable. So they're being contributed to by a lot of different people, not only AWS engineers who work on these services themselves, but also different companies that use the services. So for example, the S3 deployment, if a company A is using it and they have an idea for a usability deployment, these constructs are all open source on GitHub. And they have contributed usability fixes, bug fixes, as well as when there's a new feature, AWS engineers are all contributing to it. So this is an open source collective effort by numerous developers around the world working on these CDK construct patterns for different workflows and different resources on your AWS account. Just to give you an idea, this CDK, you'll see a huge list of packages. Most of the ones on this list right here that I highlighted, I couldn't even include the full list. These are the core constructs, but there's also a growing collection of third-party constructs as well by companies who want to create a construct that creates resources for their particular service, or just like a pattern. Like there's some really cool patterns for different types of things they might want to deploy. One of the neatest ones that I saw recently was a CDK pattern where when you add this construct in CDK, it causes your application to self-destruct after a certain period of time. So it's useful for, like, if you're deploying a test application you want to run for 30 minutes and then it just destroys itself so you stop paying for it. It'll automatically create a Lambda function and automatically create a rule, so that way the application spins up and after 30 minutes it spins down. So there's basically infinite possibilities for what you can build, and a lot of these things are already pre-built to be found on NPM, but there's still a lot more things that we can build as well. So to summarize the pros and cons of AWS Cloud Development Kit, well, I couldn't really think of many cons. I'm a big fan of CDK personally. But in terms of pros, we still have this declarative approach of creating and updating resources automatically without having to hand code things. And we have a new benefit with CDK, which is that these constructs are much higher level. So all I have to do is create one high-level construct, and it automatically creates a bunch of underlying resources all at once. So I don't have to create a bunch of things manually one by one by one. I create one overarching thing, such as a VPC construct, and it creates all of the required components underneath automatically. With CDK, multiple people can work on a CDK app at the same time. It's just code, so the same way that you would have multiple developers working on an application, you can have multiple developers working on a CDK app as well. With CDK, there's still conflict resolution, so multiple people can deploy a CDK app at the same time without conflicting with each other. And then another huge benefit of CDK is that you're developing in a familiar programming language. So far we support Python, JavaScript, TypeScript, .NET, and Java. And we're also working on Go bindings as well. So keep an eye out for that. That's upcoming. The other core benefit of CDK is that it does more than just work with the cloud. It can also help with your local development workflow as well. So it will do things like package up the website files and upload them to S3. And then last but not least, CDK is all open source and shareable and reusable on NPM. So you're benefiting from best practices that have been designed by experts from across the industry. Not only AWS engineers, but also experienced engineers who are working at a variety of different companies doing development effort and creating cloud resources. They are also building and contributing to these constructs so that you get to deploy the same patterns that they're deploying, and you know that you're deploying good production-ready infrastructure because of that. So we introduced containers, we introduced container orchestration, and now hopefully I've sold you on the idea of AWS CDK. Let's see how CDK and containerized applications combine with each other. And so just to recap, to make sure we're on the same page, the container is just a way to gather up the application code off a folder on your computer, and then I run Docker build to build a container image that has my application and all of its dependencies. And then I use Docker run to take that container image and turn it into a running container in an environment. And then to recap the container orchestration concepts, I take my container and I create a task definition which describes how I want to run it. I create a cluster, and then I either launch a standalone task, which is just a standalone container, or I launch a service, which is launch multiple containers at once and hook them up to some other resources. So these are the pieces that I want to create with my infrastructure as code. Let's see how CDK helps me to create all of these things. So there's two different levels of container abstraction that are available inside of CDK for ECS. And then the second is AWS ECS patterns. And so I'll introduce both of these. You can kind of get an idea that the ECS core one is getting 54,000 weekly downloads. ECS patterns is currently getting 13,000 weekly downloads. So there's a lot more people who are using AWS ECS core right now than ECS patterns. Most of it is because a lot of CDK is a little bit still in the early adopter phase. It's becoming more and more mainstream, but a lot of people are using the core constructs right now. The newest and latest pattern for people is the ECS patterns, though, which is currently at 13,000 weekly downloads. So to summarize the difference between these two, the core is a simplified, slightly lower level approach to defining your basic patterns for basic resources like your Docker image, your cluster, task definition, task, or service. And then ECS patterns is a higher level, more advanced system for defining a collection of things that you want to put together for a common containerized architecture. So an architecture might be something like a load balanced web service or a queue consuming application. So you have like work that goes into a queue, and then you have a worker which pulls items out of a queue. Another pattern might be, I want to run a particular container every day at this time. So ECS patterns is designed to give you a way to create an entire architecture with just one construct. So let me show you what that code looks like. So this will introduce you to the basics of CDK for containers. And the goal here being, following this, you can try to write your first CDK program in just 5 minutes. So the first pattern I want to show you is how to build a container image. So here you have this command ECS .container image from asset. So what this does is, remember the S3 construct that I showed, S3 deployment construct that I showed earlier. This is a similar construct, except what it does is it grabs your Docker file and your code off of your developer machine, and it automatically runs Docker build to package that all up into a Docker container. And then once it has a container image, it automatically provisions an ECR container registry in the cloud and automatically uploads your Docker image to the registry. So end to end, I can take my application that's on my machine and I can build it, package it up, and upload it to the cloud with just one line of code here. So this is obviously a huge time saver for development workflow. I don't have to do all the steps by hand in the command line anymore. I don't even have to write my own script to automate all of this. All I have to do is import this library and make one line of code, and it will do all of this for me. So the next level in the ECS pattern is to create the cluster to run your application. So with this command, you can see the VPC construct I introduced earlier. Now I'm adding a new construct called ecs.cluster. And so all I have to do to create a cluster to run my containers is this command, new ecs.cluster. Now I have two options here. If I want, I can stay serverless and use Fargate with this cluster. If I do that, I don't even have to add any more lines of code. If I do want to actually run on an EC2 server, though, then I can use a simple class method called add capacity. So I say cluster.addCapacity, and I specify what instance type and how many of them I want to add to the cluster. And that's all that's required in order to add 3 t2.xlarge EC2 instances to my cluster. So you can see that this interface is much simpler than writing out a lot of constructs for auto-scaling groups and clusters and scaling rules and things like that. This is automatically creating all of that for you. So now I want to show the first ECS pattern, one of my favorite ones, the load-balanced Fargate service. So this code snippet that you see here, it's only 3, 4, 5, 6, 7, 8, 9. It's only 10 lines of code here. But this is all that's required in order to create a fully functioning CDK application. So what I'm doing is I'm creating my VPC and cluster, as I showed earlier, balanced Fargate service. And I'm instantiating the service by specifying a container image that I want to build, the cluster, and how many of them I want to build. So you'll see that container image from asset. I already showed that earlier. The only thing that's new here is this ECS patterns.load-balanced Fargate service. And what this does is it automatically creates a load balancer. It automatically takes that image that has been built and uploaded, and it automatically deploys the load balancer and service connected to each other inside of my VPC. So it's just a few lines of code on my local machine, but it's doing all of this automatically for me. The next pattern I want to show is the queue consumer. This one is very useful if you have some heavy work to do. Like, let's say you're doing something like resizing images or resizing a video or something that takes a while to do. And you have a lot of these different jobs to do. Oftentimes what you'll do is you'll put them into a queue. And so you'll have one API which accepts the request to do a job, and the API puts that job into the queue, and then behind the queue you have a worker which grabs jobs off the queue and starts working on them. So there's a pattern for that built into the ECS patterns construct. It's called ECS patterns.queue processing Fargate service. And the cool thing here is that I create my queue using a simple CDK call, and then I just specify that same queue when I'm creating my Fargate service, and it will automatically establish the link between that queue, allowing my queue processing service to pull items off of that queue and work on them. And I also optionally can also easily establish an auto-scaling rule, so that way if there's more and more and more jobs backing up in the queue, there's a lot of people submitting jobs in the queue, it'll automatically scale out the number of containers. And then if the queue is empty, it'll scale in the number of containers and reduce them. So this one right here, all-time favorite, scheduled Fargate task. So a common problem that people want to solve with code is, how do I do this task and automate it to happen every day at a specific time? And if you're familiar with operating system concepts, then you'll know that there's a service called cron which does this for you. So the idea with cron is you set up a simple rule and you say every day at 5 o'clock, if the computer is running, then do this job and by running this particular command. But the problem is your computer may or may not be running. You know, if you were to set up a cron job on your own developer machine, then even if you specified you wanted to run this job every day at 5 o'clock, you would have to make sure that your computer was actually on and running at 5 o'clock in order for the job to run. And even in the cloud, if you have a single server which is running cron in order to run some code every day at 5 o'clock, we know that sometimes there are outages, sometimes there are servers that go down. Hopefully that doesn't happen. It doesn't happen often. But depending on how valuable your job is, if you're working on a job that has extremely high business value, you want to ensure that that job definitely happens every day at 5 o'clock. And one of the problems you want to solve then is, how do I make sure that even if that particular EC2 instance goes offline, or an entire availability zone goes down and my EC2 instance is killed, how do I know that for a fact that my code is going to run? So you can use Fargate in this scheduled Fargate task to have what's called high availability cron. So I just specify a schedule expression for how often I want to run my application container that has my job inside of it. And that's all I need to do. So every day at 5 o'clock, the container will be pulled out of my container registry and run inside of Fargate. And the reason why that this is super highly available and reliable is that Fargate is distributed across lots of different availability zones. And so even if one availability zone was down, there would still be capacity in another availability zone to run my container. So I know that my container is going to run somewhere every day at 5 o'clock. I don't necessarily care what machine it runs on. It's going to run on Fargate somewhere from what I ran. So you can see that this is a simple pattern, very easy to write, but it's super powerful in terms of what it can do for you to solve a common business problem in a reliable, production-ready way. So let's dive a little bit deeper now. I want to show how to do something a little bit more complicated. I showed the ECS pattern for defining a load balance service. Here's how I would define that same service using the ECS package directly instead of ECS patterns. So you can see some of those concepts I introduced earlier for the container orchestration, like the task definition. Here's how I would create a task definition using CDK. I just say task definition.add container, and I specify which container. And you can see I'm specifying manually how much memory I want my container to have. In this case, 256 megabytes of memory is all I need to run this container. And then I'm also manually adding some settings for port mapping. So I'm saying I want you to map the port 80 of my application container to port 8080 on the host. And then I'm creating a service based on that cluster and task definition. And here's how I can take use CDK code to take this exact same service I just created and attach it to a load balancer. So here I'm saying ECS EC2 service. This is creating a service using that task definition I created. And I'm also creating a load balancer by saying new ELB v2.application load balancer. And I specify internet facing is true. And so that's all I need to do in order to specify that I want to create an internet-facing load balancer that's accepting traffic from the public. So this is automatically going to create security group rules, and it's automatically going to create all the configuration I need inside my VPC for traffic to flow from the public on the internet to my load balancer and then through to my application. based on this list listener that I add, and then attaching the ECS target to that listener. So you can see this is a little bit more verbose in terms of configuration than the ECS pattern that I showed earlier. But the advantage is that I have more in-depth control of all the settings. I can control these ports directly. I can control these health check intervals and paths and timeouts directly if I want to. This is an ECS pattern that I particularly enjoy. A lot of times when you're creating a container, the container needs to connect to other resources on your account. So let's say you have a DynamoDB table, or you have an SNS topic, or you have some other AWS resource on your account that you want your code to be able to utilize. Well, if you're familiar with AWS, you know that everything has IAM rules that are required in order to authorize one thing to be able to utilize another thing on your AWS account. And this becomes a little bit tricky to configure. Sometimes people get lazy and they just create a default IAM policy that grants permission to manipulate and change anything on your AWS account. But we know that's not very safe, right? And then sometimes people go the other extreme and they create a IAM policy that's super locked down, but then they have to spend a lot of time hand managing it and worrying about, am I granting too much access to this? Going through and writing very verbose IAM policies to limit who and what applications can talk to what resources and using what actions. So CDK simplifies a lot of this by automatically creating IAM policies for you and for your resources based on simple statements that you define. So here I've created an ECS service using the EC2 task definition construct. And I have a DynamoDB table and an SNS topic that I want to grant my containerized application access to. So all I have to do is say my DynamoDB table that grant read-write data to the task definitions task role. And once again, this task role is automatically created. It's automatically managed by CDK. So this grant read-write statement automatically creates the IAM policy rules that authorize my service to talk to DynamoDB. And the same thing goes for that SNS topic as well. I can say grant publish to automatically give my ECS service permission to publish to the topic. So to summarize things that CDK can automate away for you, CDK automatically creates security groups and minimum containers. CDK automatically creates IAM roles for your containers. So that allows you to easily establish minimal access rules, so that way your container can talk to only the resources that it needs to talk to. AWS CDK can even automate automatically building your container image and pushing it for you. And it'll automatically creating a load balancer and attaching it to your service for you via that ECS pattern. So to summarize the difference between the two, you can kind of see as an overview the difference in code length here. So if I'm using AWS ECS patterns, all I have is the simple 5 lines of code to create a load balanced Fargate service. If I use AWS ECS directly, I have a little bit more of verbose, probably 30 lines there of code, but I have more direct control over the underlying settings of what I'm creating in terms of my containerized application. So if you're just starting out, I would recommend pulling down the AWS ECS patterns and starting with those, because like I said, all you have to do is write 5 lines and you have your service up and running. If you're a more experienced user or you just want to dive a little bit deeper, you can check out the AWS ECS constructs to stay a little bit more mid-level and control everything yourself. But either way, you're removing a lot of abstraction, you're removing a lot of boilerplate, because both of these code samples here would expand to about 2,000 lines of CloudFormation directly. And if you were to go around and click around in the console manually, it would take you a long time to configure all these things manually in the console, and chances are you would make mistakes trying to get everything typed in and clicked around by hand. So before I finish up, I want to give a shout out to one other thing, which is AWS CDK for Kubernetes. So I spent a lot of time talking about the AWS native ECS solutions, but there's also AWS CDK for Kubernetes, which is really an awesome project. I hope if I get a chance, if y'all have me back for this meetup in the future, I can present about CDK for Kubernetes as well in the future, because it's a very cool project as well if you decide to use Kubernetes as your container orchestrator instead of ECS. So thanks a lot for following along with this presentation, and happy to take any questions if we have time.
Thank you very much, Nathan. That was a very informative session. Yes, guys, I think we can open for Q&A. So you can unmute yourself and ask the question.
Hi, Nathan. This is Sharif Khan. I have one question. Is it possible to pass a context object? For instance, the account details, and if you take in the images, the ECR images, the tag, because when you version tags, you have different versions.
Mm-hmm.
How does that happen?
Yeah, so that's a good question. So let me see if I can show you the in CDK. So basically, what happens is CDK automatically manages that for you. So it creates a new version of your container image each time you push. Let me see. I'm not sure if it's documented here. I can always also just show you on ECS directly here in my AWS console. So if I go to repositories and I click on a repository that's being managed by CDK, let's say, for example, which is a good one. I think this one is a good one. You can see that it's automatically created different versions that correspond to each version of my code. So all of this is actually self-managed by CDK. All I have to do is say build and CDK deploy, and it'll automatically build a new container image. If it's seen that my code changed on disk, it'll automatically push it to a different tag for me. Does that answer the question?
Yeah. Does it support artifact promotion if I want to promote it? So let's say I have 2 different accounts for 2 different environments. Or let's say I have 2 different clusters for 2 different environments.
Not directly. More complicated.
Okay.
Generally, what I see people do is they just rebuild the container image using the exact same Docker file from the exact same code commit. But it would be possible to actually have the container image being built in one stack and then have 2 other stacks. So you could have like a base stack which builds the container image, and you can have a test QA environment stack which deploys that version of the container image. And then you would have a production stack, which you can then modify to deploy the same version of the container image. I personally think it's a little bit more easy to just rebuild it again from scratch rather than trying to promote the exact same one. But it definitely is possible. I think we need to do a little bit of work in CDK to make it a little bit easier so that we don't have to use 3 stacks. Okay. So definitely open an issue on the AWS CDK GitHub if you're interested in this particular feature, and it'll help us track that. Or maybe I'll give it a shout out to the AWS ECS team that's working on CDK as well.
Yeah, that's an interesting feature if it's in place. And
sure.
The CDK itself is looking a lot promising the way it is now.
I'm glad to hear that, and I want to show that the documentation here too. We got a pretty good documentation site, so you get an idea of all the different patterns that are available here. The AWS ECS pattern that I was just showing as well. So if you do want to get started with CDK, these documentation are pretty friendly. It's not your default AWS documentation site. It's got quite a bit of detail here, and every single AWS service that you can think of.
Yeah, the 10 lines to set up a load balanced Fargate was mind blowing, because I know how hard it is to set it up manually or write the cloud formation stack.
Yeah. Like I said, this like 10 lines or so expands to about 2,000 lines of cloud formation in total.
Thank you.
So guys, are there any more questions? You can unmute yourself and ask. So in the meantime, Nathan, like, for developing serverless application that use AWS Lambda and API Gateway, so those serverless applications and AWS offers SAM and Amplify, and also, we have serverless framework, those things as well. So what is your opinion, like, since this CDK is quite promising, like, as well as for the containers, is there a way that we can easily use it for AWS Lambda and API Gateway, DynamoDB, that stack as well?
Yeah, so you absolutely can. You can use it for Lambda as well. So here I just brought up. Let me zoom in on this. Just it might be actually be hard to see over the thing. So we have multiple support for Lambda, including let me see where is it? There we have a Lambda API Gateway construct, which is higher level. Let me see. Is this the one? Yeah, so there's one that's very cool. It's called Lambda REST API. And let me see if there's a better example here in the overview. So it does a lot of the same things that that SAM does. I would say the difference is if you're familiar with serverless SAM or with some of these other providers, they tend to work really well for Lambda and basic REST APIs defined using API Gateway. But they tend to leave a lot of the other things, such as DynamoDB tables and other resources on your account, to plain CloudFormation. So that's not horrible, but you end up having a sort of serverless tool that automates away part of it for the Lambda compute environment, but you still have to hand write a lot of the other things yourself or hand create them in the console. So the goal with CDK is that it's all encompassing. Every single type of resource on your AWS account is supported, and the goal is to have higher level methods for everything. So whether that's Lambda or containers or you can think of, is all supported in CDK. So I would use CDK for the larger overarching picture when I have an architecture which is more complex, and I know that, for example, some things will be running containers, some things will be in Lambda, some things will be machine learning, and some things will be like on straight EC2. Whatever is more complex. Versus if I know that all I'm ever going to be using is Lambda, and I just want the most simple Lambda flow, then I would consider using a SAM or one of those tools as well. So really, it depends on whether you're all in entirely on Lambda, or whether you're going to have a more hybrid environment that has different types of resources. Because SAM is not going to help you with containers, for example. It's not going to help you with a lot of the other services, versus CDK can do all of those things.
Yeah, I agree with you profoundly. Like, in developing enterprise application, it's not just the serverless backend. We have hybrid, like the containers and ECS, Fargate, that's aspects, as well as the total serverless, the Lambda and API gateway, maybe AppSync, and it's all almost a combination of these stacks. I think if we have some kind of a library that you just showed, ECS patterns, another abstraction on top of the core services, that would be really amazing, because we just saw how easy it is to create that container stack you just showed us. So hopefully we will also see some patterns.
There's another pattern that I want to create at some point, which is a pattern to put together, for example, Lambdas and containers inside the same API. What I want to do is I want to have like one domain and then have it split off, and then have some requests served by Lambda, some requests served by containers, some requests served by maybe it could just be like out of an S3 bucket. But if you think about it, there's so many different types of things that are required for a production service to run. Like some things are just static website. Some things have like Java code. Some things are JavaScript code that can run in Lambda. And you want to glue all those pieces together to make your overall website. And I think that's where something like CDK will really shine.